Hi, welcome you all to An Academy. An Academy is the India's largest online learning platform. Now, these are the different about myself. I G Venkatrao. I have total 16 years of teaching experience. So far, I mentored 60,000 plus students for their GATE examination. And at present, I am pursuing my PhD from JNTU Kakinada in VLSA domain. First, we check how to get this An Academy learning app. If you have this app, it's okay. Otherwise, please install this app. Just go to your Play Store, type An Academy in that, you get this app. Now double click on this install button. Once double clicking on this install button, it will install the An Academy learning app in your device. Once you open the device, what are the different courses available in An Academy and who are the top educators handling the subjects in each course, you will get that information. Here are the few top educators from An Academy. Here. Now, I'm happy to say that we started two new batches for electrical and electronic students from January 18th. Both was all started from 18th of January. First one is Varvi batch for GATE 2023 for electrical students. These are the few top educators handling this batch. And same Varvi batch for ECE students. Now this time it is for GATE 2023. It was started from 18th of January. And there is a Spark batch for GATE 2022. It was already started from 18th of January for electrical students. And there is another Spark batch for ECE students this time for GATE 2022. It was already started from 18th of January. Don't forget to use my code VRAV10 during subscription. Okay, and just before we got information that the new batch is going to be started for ECE and electrical students from February 1st onwards because of the request from so many requests from the students. After 18, we got so many requests from the students. Okay, so for their request, they accepted their request, and new batch is going to started from 1st of January. Now there is a evolve batch for civil engineering for GATE 2022. These are the few of the top educators handling the civil engineering subjects. This batch is going to start from 25th of January. Now don't forget to use my code VRAV10 during subscription to get 10% off discount. And this is for GATE 2023 SN batch, same for civil engineering. So these are the few top educators from that. So don't forget to use my code VRAV10 during subscription. Next, there is a Evolve batch for chemical engineering students for GATE 2022. So it is also started from 25th of January. Don't forget to use my code VRAV10 during subscription. And here I want to inform one more important thing, that is outside it is very difficult to get the chemical engineering training. Okay, so you can thank to An Academy for providing this facility to you. Now next, mechanical engineering. There is a Evolve batch for GATE 2022. Now these are the few of the top educators from An Academy to handling these subjects in mechanical engineering. And again, there is a mechanical department for GATE 2023. This is Ascend batch. Okay, these are the top educators who are handling the subjects in mechanical engineering. And please don't forget to use my code VRAV10 during subscription. Okay, and by using my code you get 10% discount. Here I'm writing my code. Don't forget to use my code. Okay, now this batch is going to start from 25th of January. Now, so these are the different disciplines available from GATE Academy for GATE and engineering service aspirants: mechanical engineering, electrical, civil, production and industrial, instrumentation, computer science and IT departments, ECE, chemical engineering, and rare conditions you get the instrumentation. So now in an academy there are two plans. Plus plan is the basic plan. Basic plan. Basic plan with personal coach. You have to join Iconic batch. Iconic subscription you have to take. And from both the cases you get the classes from best educators. So there is a interactive live classes, structured courses and PDFs. Okay, live tests and quizzes you can get. Okay, you can get so many benefits. Okay, now after live tests and quizzes for Iconic batch, okay, after completion of your writing examination, they will check the your answer sheet. Okay, and from that they will analyze the topics where you are strong and where you need improvement. Okay, after that, based on your after analysis of your paper, based on that they will prepare a proper personal study plan to you. Personal study planner to you. This is for individual. At the same time, after completion of that, directly you can interact faculty personally. Now you get the personal coaching. Okay, if you are joining in an outside institutions, it is very difficult to get the personal coaching. Personal coaching in the sense, it is very difficult to interact with even faculty also. Hardly you get during lunchtime, you get hardly 5 to 10 minutes interaction, personal interaction. But here, that problem is not there. You can interact personally. Okay, now proper study plan they will provide, and personalized test analysis what I mentioned here, and they prepare proper study material to you and they will forward that material to you. Okay, by preparing all these things, okay, if you follow proper study planner and taking the suggestions from the faculty, okay, personally you are contacting the faculty and taking the clarifying your doubts, by following all this, definitely you will get good result in your examination. Okay, next, say about plus plan. So these are the subscriptions for 1 month subscription, 3 month subscription, 6 months, 12 months, 18 months and 24 months. Okay, by using my code VRAO10 during subscription, you get the 10% discount. Okay, and my advice is don't join these, don't join 1 month, 3 month subscriptions. Give minimum subscription of 1 year, then it is useful. Within 1 month or 3 months you can't complete your complete syllabus. Okay, from outside we complete, but what about the student point of view from your side? Okay, so give first priority to join minimum 1 year course. Once you join 1 year, then each and every point you can get clearly. Okay, then there is a scope for getting better result. So by using code you get the 10% discount. It is without discount it is 30,250. After getting discount it became 27,225 rupees. Okay, next there is a Iconic plan. So for in Iconic plan there are two subscriptions, 12-month subscription one, other one is a 24-month subscription. Okay, for 12-month subscription, so after getting discount you have to pay 45,225 rupees. In 12-month subscription, in Iconic subscription you are going to getting the personal coach. Okay, they will continuously monitor your development. Okay, they prepare a sheet and day to day they will forward that information to you. Okay, in which topic, in which subject, okay, where you need to put more efforts for getting a best result. Okay, they will guide you time to time. So during subscription, don't forget to use my code VRAO10. Okay, students who are willing or interested getting a personal coaching, okay, try to join in the Iconic plan. Okay, and definitely you get a maximum benefits compared to other things. You get a maximum benefits from this. And the most important thing is at outside situation is not good at present. Okay, but some of them are saying it is a pandemic. There is no pandemic. Pandemic is gone. But please don't take any choice. Okay, because it is our life. Don't take any choice. Please stay at your home. Okay, but whatever thing is happened at outside, your learning process should continue. Learning process should not stop. It should continue. Okay, now due to this pandemic, we are unable to move outside. Okay, try to give highest priority to join in Iconic plan in an academy. Okay, now if you compare this amount with the traveling amount for if you join somewhere to taking the training, okay, for traveling expenditure plus, so during class work you need to take the food outside, by including all these things, for that, but that amount only is going to be 20,000 plus. Okay, so that means more or less it is a 50% off in this, and you need to pay some more thing to that institute. You need to pay some more amount. Okay, just calculate once, sit and calculate all these things. Okay, and take a good decision, and that decision should change your life. You should be at a top level. Okay, please change your life, change your take a good decision to change your life, and that life should be a top level. Okay, now we are going to continue the equation. So far we covered so many topics in semiconductors. First we define what is semiconductor and what is the importance of learning about a semiconductor and electronics engineer. What is our motive in an electronic device? Our motive in electronic device is to operate that with a controllable current flow in a device is our motive. Okay, and after that, how to control the amount of charge carriers in a material, in a semiconductor. Once your number of charge carriers are under your control, conduction also under your control. Now if you take a semiconductor, in semiconductor two types of charge carriers, majority charge carriers and minority charge carriers. Okay, now controlling means you should be in a position to increase and decrease the number of charge carriers. Now in a semiconductor, to increase the majority charge carriers, we need to add more amount of doping. So by increasing amount of doping, majority charge carrier concentration can be increased. Okay, next, to increase minority carrier concentration, temperature has to be increased, but that case not using practically. So only our concentration is completely on majority charge carriers. Rare conditions we give priority to minority charge carriers. Okay, and after that we went for energy band diagram. By increasing amount of doping, what about its energy band diagram? How it is changed? What is the Fermi energy level? Different equations we derived for a intrinsic semiconductor, N-type semiconductor and P-type semiconductor. Okay, and we done some problems also on that. After that we went for charge neutrality in a semiconductor. This is very important point. You can take any semiconductor, it may be intrinsic semiconductor, extrinsic semiconductor, whatever it is electrically neutral. A semiconductor is electrically neutral. Okay, by applying that concept on a semiconductor, we calculated amount of majority charge carriers and amount of minority charge carriers in a semiconductor for a given amount of doping. We calculated amount of majority charge carriers and minority charge carriers for a given amount of doping. Okay, by knowing the intrinsic carrier concentration Ni. Okay, those things we completed. And after that, once the charge carriers are under your control, once carrier concentration is under your control, next thing is by using those charge carriers. Now, that conduction is, we mentioned in the terms of charge current density. By the movement of charge carriers, we are getting the current density. Now, there are two types of current densities: drift current density and diffusion current density. Drift current density and diffusion current density. Okay, before going to continue the equation, just 1 minute I am going to writing the equations for drift and diffusion current densities. At the same time, current density for electrons and current density for holes. Okay, here first one is drift current density. Drift current density. So we get this, just take a semiconductor. Now an external potential is applied to this, potential difference. So it is positive, it is negative. That means this side it became a positive and this side it became negative charge. That means externally we applied an electric field. Due to this electric field, whatever the charge carriers present in this, these charge carriers are moving in a proper direction. Okay, so holes are moving in this direction and electrons are moving in this direction. Now once charge carriers are in proper direction, we get the conduction and current. This movement is called drift movement, and this current is called drift current, and current density, current per unit area, is called drift current density. Okay, now J drift by electrons n type is, at the same time we are going to write J drift by hole P. Okay, so drift current density is N into Q into mu N into applied electric field. Applied electric field, and here it is P into Q into mu P into applied electric field. Next one is diffusion current density. Diffusion current density. Diffusion current density. Diffusion current density. Here I am taking the semiconductor. These are the minority charge carriers of a semiconductor. At one end, I am going to be illuminating this end with light, exposing with light. Once it is exposed to light, so many covalent bonds are breaking. Now electron hole pairs are generated. At the same time, due to that breaking of covalent bonds, minority carrier concentration is increasing. Now at this point, more number of minority charge carriers. At this point, less number of minority charge carriers. We called it as diffusion, concentration gradient, change in concentration with respect to distance. Due to this, carriers are moving from high concentration point to low concentration point. That movement is called diffusion movement. That movement is called as diffusion moment. Okay, now that is the current due to this diffusion moment is diffusion current, and the density is diffusion current density. Now I am writing the equation for this. Diffusion current density by electrons equal to dn into q into dn by dx. Okay, similarly J diffusion by hole P is minus dp into q into dp by dx. From this two we can write total current density by electrons is J drift by electrons plus J diffusion by electrons okay, now which is equals to, we know J drift value, it is a n into q into mu n into applied electric field plus J diffusion is dn into q into dn by dx. So now we are going to using this equation in our continuity equation. Similarly, I am going to writing the equation for current density by hole. So Jn is Jp is J drift holes plus J diffusion holes. Density is completed. Now I am moving to continuity equation. See, continuity equation is using in different fields. It is using in thermodynamics, fluid mechanics, electromagnetic fields, and semiconductors also. In semiconductors also we are using this. Okay. Now, how we are using this? First of all, continuity equation is going to explain us about conservation of a particular parameter. Conservation of a particular parameter. According to law of conservation, energy cannot be created nor destroyed. Okay. Charge cannot be created nor destroyed. Mass cannot be create or destroy. Okay. So like this, conservation of a particular parameter. Now that particular parameter what we mention here is it cannot be created nor destroyed. So it can transfer from one form to another form only. Okay, in this semiconductor I am going to using this. In semiconductor this parameter is charge, conservation of charge, and in electromagnetic fields it is conservation of energy, and in fluid mechanics it is conservation of flow of mass or mass rate. Okay, so this is the continuity equation briefly. So it explains about conservation of charge in semiconductors point of view. Here our intention is to learn or to apply continuity equation in semiconductors. Okay, so in semiconductor it is nothing but a conservation of charge. Okay, this was asked previously in IAS. Continuity equation explains about law of conservation of charge. Okay, now I am applying this one to a semiconductor. I am taking a semiconducting bar here. Now the length of the bar I am taking is, let us take the length of the bar is L. Length of the bar is L and cross sectional area is A. Its cross sectional area is A. Okay, this is semiconducting bar, sir. It is a semiconductor. For my analysis purpose, I am going to taking a small fractional part in that. We called it in generally infinitesimal part. A small fractional part. Okay. Now, I am taking a small part in that. Now, this is going to be the small fractional part in this. Okay. So this is the small fractional part of it. Okay, here I mentioned this one. This is the small fractional part. And it's a cross-sectional area also same as cross-sectional area of this bar. This is the small bar. Small part, small volume I am taking. Okay, and the cross-sectional area of this one is A. Now the small volume also having a cross-sectional area of A, but its length is, this is the point X and this is small delta X, small fraction, it is a small part delta X. Now it became X plus delta X, X plus delta X. Okay, and for my easy understanding purpose, I am going to separating this block from this, separating this small volume from this whole block. Okay, and here. Okay, before going to that, I want to tell a story to you. See this. Let us take a pond. So this is a water pond. Here, this is a pond. I want to know the amount of water in that. Okay, amount of water in that. I want that information. To get the amount of water, so amount of water, my intention is to get the amount of water in pond. Amount of water or net amount of water equals to, there is a inlet to this. Now water is coming from outside. This is inlet. This is the inflow. This is a inflow, and this is outflow. Okay, this is inflow and it is outflow. Now net amount of water equals to inflow minus outflow. Inflow minus outflow. So inflow of water minus outflow of water. Outflow of water. Next, is there any additional options to get a water into that or to moving water out of it? For example, if it is a raining session, then you get some water in the form of a rain. Let us take it as a clouds. Now in the form of rain you get some water. So this raining water is plus to us. It should add plus rainwater, rainwater. Okay, for example, there is a sunny day. On the day, sunny day, there is a, okay, it's too much heat at outside. Now, due to this heat, whatever the water present in the pond, some of the water is evaporated. Evaporated. Okay, now we need to remove this. Now, minus evaporated water. Evaporated water. That is the net amount of water in a pond. Inflow water, outflow water, rainwater, evaporated water. Okay. Now I am applying this one to my continuity equation to get net increase of charge in a semiconductor. Net increase of charge in a whatever the infinitesimal or a small volume we taken, in that small volume, okay, the amount of charge increment I want to get. For that I am going to applying this concept. Simple. So amount of change, so total charge, increment in charge equals to charge entering into the volume, entering minus charge leaving, because it is inflow water, inflow charge entering, outflow charge leaving, plus rainwater. And if you take your semiconductor, okay, once we keep our semiconductor as it is here, what happens is there is a continuous generation of charge carriers takes place. Generation and recombination is a continuous process in a semiconductor. Okay, generation and recombination is a continuous process in a semiconductor. Already we completed that in generation and recombination of charge carriers. Okay, now so generation rate in the volume minus recombination rate in the volume. Okay, so rainwater, it is addition to that. That's why it is generation, evaporated water, recombination, it is losing the water. So now I am going to applying this concept to my semiconductor to get the increment in charge in a small volume. Okay, now I am going to writing the equations for charge entering, charge leaving, generation rate within the volume, and recombination rate within the volume. One by one equations I will write, and after that I will add all the equations, all the parts. Next, now see, when the specimen is subjected to an external field, the net change in charge, see, whatever the specimen there we taken previously, this is semiconductor specimen we taken. Okay, when it is subjected to a external field, that means an outside, I am going to applying some voltage to this. Now current is flowing in this. Once current is flowing in the sense, charge carriers are moving from one point to another point. Once charge carriers are moving, there is a change in charge taking place. Charge is moving from one point to another point. In this sense, charge is changing. Now I am taking this infinitesimal small volume. Okay, within this volume, what we taken, our volume is just wait. Yeah, now this is our volume. This is x and this is x plus delta x. Okay, delta x plus delta x. Now with respect to time, how much number of electrons are entering and how many number of electrons are leaving, that is I want to know first. Now I am representing that one by this one. Dou n by dou t is net increase in electron concentration with respect to time. Net increase, we need net change in the charge. I am taking that charge is increasing within this volume. The net increase or net change in charge. Okay, change in electron concentration first I am taking. Okay, net increase in electron concentration with respect to time. Okay, now I am applying, this is electron concentration you are saying. Electron concentration means number of electrons per unit volume. That is the concentration, N. Okay, but I want total number of electrons. Total number of electrons. That means total number of electrons within this unit volume, within this volume. So the volume is, cross-sectional area is A. The volume of this one is, this is a delta x. Now its volume is, the volume what we have, its volume is area into delta x, length. That's why I am going to multiplying this with volume, A into delta x. After multiplying this one with volume A into dx, it became number of electrons increase in the volume. Increase in the volume. Okay, increase in the volume with respect to time. Now next, now I am applying that one to this. See here. So the same fractional volume I am taking here. It is x plus dx. Now its a cross sectional area is A. Now it is delta x. We know that. Therefore, dou n by dou t of A dx is equals to number of electrons entering into the volume. Number of electrons entering into the volume minus number of electrons leaving the volume. Number of electrons leaving the volume plus generation rate in the volume. Generation rate in the volume minus recombination rate in the volume. Recombination rate in the volume. Okay. Just I am going to combining all these things here. That is my intention. By combining all this, finally I get a net change in the charge. Next. Now I am going to writing the equation for one after another. See, we know that current I is equals to NQ by T. Okay, because we are defining current is a rate of flow of charge. Rate of flow of charge. Now let us take total N number of charges you have. Okay, each charge having a charge value of Q, N number of carriers, each having a charge Q on that. Now I is NQ by T we can write. At the same time, current density we are writing it as I by A. I by A. Now I am taking this value of I and substituting that one in this equation. Now J became, I means NQ by T by A. This is your J. Here we need number of charge carriers. Previously we defined number of electrons entering into the volume per second. That means amount of charge entering into the volume per second. Okay, now that's why number of charge carriers entering or leaving, whatever it is, entering or leaving per second. That means now here my intention is to derive a basic equation. What is the basic equation? Okay, after that, with respect to that point, I will change my basic equation into that. Okay, now n by t is j into, taking this area this side, q this side, j into a by q, j into a by q. That is the basic equation for number of charge carriers entering or leaving per second. Okay, now here I have written all the equations what we have. First I am going to see, previously we derived an equation there, this one, it is a ja by q. Okay, now okay, this is our small volume what we have. Small volume, small volume, and this is x, this is x plus delta x, and its cross sectional area is a. Okay, here our in, we know we need ja by q. Previously we written that number of charge carriers entering or leaving per second is n by t is ja by q. Now ja by q. Now at this point I am taking electrons, so electrons, now I am writing this here, it is j n of x with respect to distance. Here current density is j n of x plus delta x, j n of x, and here it is j n of x plus delta x. Okay, now entering, first I am writing the entering charge or entering electrons. Entering charge entering, or simply is jn of x, here it is entering, jn of x into area by q. Okay, see, we need this number of electrons entering into the volume per second. Okay, now number of electrons, here we are taken clearly it is electron, that's why I am going to adding the negative polarity to this. Okay, so this is finally number of electrons entering into the volume per second. Number of electrons entering into the volume per second. Okay, similarly I am taking leaving, number of electrons leaving the volume per second equals to, this is the current density, j n of x plus delta x into area by minus q. Don't forget to use negative because electrons here, charge of the electron is negative. Okay, similarly for holes, okay, if I am using holes, Now for holes, this is for electrons. For holes, number of holes entering into the volume per second equals to J P of x into area by charge of a hole is taken as positive Q. And similarly, I am going to writing the number of holes leaving the volume per second. Number of holes leaving the volume per second equals to Jp of x plus delta x into A by Q. Okay, and we can write generation rate and recombination rate is left. Okay, now for electrons and holes, generation rate we can write rate in the volume. Generation rate is G. Okay, now in the volume, the given volume is A into delta x. This is the given volume. So within that complete volume, generation rate is A into G into A dx. A dx is the volume. Similarly, recombination rate in the volume. Recombination rate in the volume is R into A into dx, delta x volume. Okay, now these things has to be substituted in the previous equation what we derived. See, previously we've written one equation. This is the equation we've written. This is the main equation, sir. It is very, very important. Now we are going to substituting those things, those values in this equation. Okay, next. Yeah, see, Jn of x into A by minus Q, these are the number of electrons entering into the volume per second. Number of holes entering into the volume per second is Jp of x into A by Q. Number of electrons leaving the volume per second is Jn of x plus delta x into A by minus Q, because they are electrons. Number of holes leaving the volume per second is Jp of x plus dx delta x into A by Q. And generation rate in the volume is G into delta x into A, and recombination rate is R into delta x into A. This is the recombination rate. Now I am going to be substituting those in equation. Okay, now let us, I am taking the n-type semiconductor. Later we apply this one to the p-type semiconductor also. For n-type semiconductor, dou n by dou t into A dx is, delta x is, it is entering charge. Just before we written Jn of x into A by minus Q, minus leaving charge Jn into x plus delta x into A by minus Q, plus generation rate of electrons. So I am taking it as a Gn into A into dx, minus recombination rate in the volume. Recombination rate is Rn, volume is A into dx, delta x. Okay, now I am simplifying this. Whatever the delta x here we have, this delta x, this delta x, this delta x gets cancelled. Now it became delta x here and it became delta x here. At the same time, this negative into negative, it became a positive. And in this 2, I am taking 1 by q common. Now, by simplifying, you got dou n by dou t is this much. Jn of x into a by minus q into dx plus, it is plus, minus into minus plus. Jn of x plus delta x into a by minus q into delta x plus gn, generation rate, minus recombination rate Rn. Now, by simplification, I am taking 1 by q common in this 2. Now it is Jn of x plus delta x minus Jn of x by delta x plus Gn minus delta n. Okay. This is the dou n by dou t. Next one, I am simplifying that equation again. See, whatever the small volume here we taken, this is the equation with respect to distance here, and we need to mention with respect to time also. But see, at volume x, electrons entering, and at volume x plus, at a distance of x plus dx delta x, electrons are leaving. Both the things happened at time t itself, because this is a very small value, small volume, okay, small infinitesimal part. Okay, both are taking place at a time t. Okay, you observed or not, Jn of x comma t, now change in current density due to electrons with respect to distance and time, and here also distance and time, okay, by delta x plus Gn minus Rn. Now I am going to applying limit, because you are saying this is the delta x, and this delta x is very small in the sense it is approximately 0, okay, not exactly 0, approximately 0, then only it is a very small value. That's why I am going to applying the limit on this. Now, limit delta x tends to 0, dou n by dou t equals to limit delta x tends to 0. This is the value of dou n by dou t. I am writing this equation as it is here. It is independent of delta x, that's why I am taking these two as it is. Next, here I am applying this delta x. So delta x, limit delta x tends to 0, and 1 by q also a constant. Limit delta x tends to 0, Jn of x plus delta x comma t minus Jn of x comma t by delta x. This is the basic equation or definition of a partial differentiation. That's why now I am separating 1 by q from this, and the remaining, except 1 by q in this part, remaining I am writing simply a partial fraction of Jn. So dou Jn by dou x, simple, dou Jn by dou x. Okay, now limit delta x tends to 0, dou n by dou t, I am taking it as now dou n by dou t. So final equation for dou n by dou t is 1 by q into dou Jn by dou x plus generation rate minus recombination rate. So that is the equation. Now, but we know the equation for current density due to electrons. So we have Jn is nothing but a drift current density. This is the drift part, and this is the diffusion part. Okay, this is the total current density. Now I am taking this current density Jn value and substituting in the previous equation. What we have, our previous equation is dou n by dou t equals to 1 by q into dou Jn by dou x plus generation rate minus recombination rate. This is our equation. Now I am writing this in place of Jn, I am substituting this one, Qn into mu n e plus Q into Dn into Qn by Qa, dou n by dou x. Just take this and substitute here. Now I am substituting. So these two are as it is. Now it is 1 by q into qn into mu n into e plus q dn into dou n by dou x. Both are same. Okay. Now I am going to differentiate in this, partial differentiate in this with respect to dou x. Here q constant, mobility also constant, electric field is changing and n is also changing. Now I am writing that one is, see, n into, see, this q here, this q and this q gets cancelled. Okay, now only n is constant, mu n is constant. Now see this, dou by dou x of n into mu n into e plus dou n in dn into dou n by dou x plus gn minus rn. Now I am going to differentiating this first, later this, n into mu n into dou e by dou x plus n into e dou mu n, sorry, mu n into e dou n by dou x. So mu n into e dou n by dou x. Okay. Next, plus dn, different diffusion coefficient, into dou by dou x of dou n by dou x. It is a dou square n by dou x square plus gn minus rn over. Okay, this is the final equation of a continuity equation for electrons. Okay, now I am going to doing the same thing for holes. Okay, that means for p-type semiconductor. This is for n-type. Now I am moving to p-type semiconductor. So p-type semiconductor. P-type semiconductor. So for p-type semiconductor, dou p by dou t is, instead of dou n by dou t, I am taking dou p by dou t into a into dx equals to, okay, j p of x entering into area by q, charge is positive, minus leaving charge, j p of x plus delta x into a by q positive plus generation rate gp into area into delta x, it is volume, minus rp recombination rate into volume, area into delta x. This is the basic equation. Okay, now I am going to work out on this, and finally I am going to get the dou p by dou t. Now here first delta x is going to be cancelling this delta x. Okay, later I cancel that, taking this delta x this side. Now it became dou p by dou t equals to into a equals to, okay, I do one thing, I am cancelling a. Yeah, you can cancel a, it is in all parts. Now dou p by dou t into delta x is 1 by q into jp of x minus jp of x plus delta x plus gp into delta x and minus rp into delta x. Now whatever the delta x here we have, I am taking this delta x this side. Okay, now these two delta x gets cancelled here, and Here you can add delta x. Now we can write dou p by dou t is equal to I am taking minus common in this. Now it is minus 1 by q into jp of x plus delta x minus jp of x by delta x plus gp minus rp. Okay. Now I am adding the time factor to this time. Now dou p by dou t is equals to minus 1 by q into jp of x plus delta x comma t minus jp of x comma t by delta x plus generation rate minus recombination rate. Okay. Now here I am taking the limits because that volume what we are taking is very small, we are expecting. Okay, small volume means smallest value is approximately equals to 0. This is a delta x. Now limit delta x tends to 0, dou p by dou t is equal to limit delta x tends to 0 minus 1 by q into jp of x plus delta x comma t minus jp of x comma t by delta x plus gp minus rp. Okay. Now, so I'm going to next slide. So our equation is limit delta x tends to 0, dou p by dou t equals to limit delta x tends to 0. Here we have minus 1 by q into jp of x plus delta x comma t minus jp of x by delta x plus gp generation rate minus rp recombination rate. Now I am taking this minus 1 by q taking outside and taking this limit into this side. Now it is limit delta x tends to 0, dou p by dou t is minus 1 by q into jp of x plus delta x comma t minus jp of x by delta x plus gp minus rp. Okay. Now, sorry, here limit is there, sir. Sorry, forgot that. Here equals to minus 1 by q into limit delta x tends to 0. This part of the equation is nothing but a basic definition for partial differentiation. Now we can write it as limit delta x tends to 0, dou p by dou t is dou p by dou t equals to minus 1 by q into, this is dou jp by dou x plus generation rate minus recombination rate. This is the standard equation. Now we know the Jp, current density of a p-type semiconductor. Okay, now I am going to substituting that value here. Therefore, finally we got dou p by dou t equals to minus 1 by q into dou jp by dou x plus gp generation rate minus recombination rate rp. Now, but we know jp value. Jp is nothing but a drift plus diffusion. So drift current is P into Q into mu P into E, applied electric field, minus diffusion current plus diffusion current density is minus dP into Q into dP by dx. Okay, now I am taking this one, substituting here. Therefore dou P by dou T is equal to minus 1 by Q into dou by dou x of Jp value, P into Q into mu P into E minus dP into, so you can take either d or dou, no problem. I am changing this one into a dou P by dou x, sorry, okay, dou P by dou x. Now into dou P by dou x plus Gp minus Rp. Okay, now this Q and this Q, sorry, here Q is there, dP into Q into dou P by dou x, and this Q gets cancelled. Therefore it is minus dou by dou x of dou by dou x of P into mu P into E minus dP into dou P by dou x plus Gp minus Rp. This is our expression. Okay, now I am simplifying. Here mu P is constant, here dP is constant, so these two are constants, no need to apply the partial differentiation on this, which is a dou P by dou T. Now dou P by dou T is, finally you can write mu P constant, mu P into, sorry, here minus is there, negative, minus mu P into P in E into dou P by dou X plus P into dou E by dou X. Dou E by dou X. Okay. Dou E by dou X. This part is completed. This minus into minus, it is plus dp into dou by dou x of dou p by dou x. It is a dou square p by dou x square plus gp minus rp. Minus rp. Now I am going to simplifying this. Therefore, dou p by dou t is minus mu p into E into dou p by dou x. Next, minus mu p into P dou E by dou x plus dp into dou square P by dou x square plus gp minus rp. This is the continuity equation for a p-type semiconductor. Continuity equation for a p-type semiconductor. Just before we derived an equation for continuity equation for n-type semiconductor. Okay. There you got this is positive. Here it is negative. So this is about your continuity equation. Okay, simply it explains about conservation of charge in a semiconductor or law of conservation of charge. Charge cannot be created nor destroyed. Okay, this is continuity equation. Okay, now we are going to a small topic, that is this is our semiconductor. I am applying a voltage like this. Let us take, clearly I am giving p-type semiconductor. P-type semiconductor. This side I am applying positive charge, this side I am applying negative charge. It results holes are moving from this side to this side. Holes are moving. Now you get the conduction also the same side. Okay. Now my point is, whatever the semiconductor here you placed, I am going to representing this semiconductor in terms of its energy band diagram. The energy band diagram of a p-type semiconductor is like this. This EC EV. Okay, and at center you have a intrinsic Fermi energy level EFI or EI I am taking for simplification, and this is the EV. This is for p-type semiconductor. Okay, now if you take similarly n-type semiconductor, your n-type semiconductor energy band diagram is like this. This is the Fermi energy level of it. So EC, EFN and EV at center approximately EFI. It's okay. Okay. Now this is the energy band diagram of a semiconductor under thermal equilibrium. They did not applied any external voltage on this. Okay, they did not applied any external voltage. Okay, so my semiconductor is like this. This is my semiconductor. The energy band diagram of my semiconductor is like this for P type. For N type, it is like this. Now, here the case is, whatever the semiconductor here I have, it is subjected to external voltage. External voltage V. Okay, when it is subjected to external voltage, the energy levels what we have are going to be bending. Energy levels are going to be bending. Okay, now just to get the electric field in that, for this is positive, at this end you apply, at this end it is negative. Okay, now electric field is away from positive towards negative. Okay, now once electric field is directed this side. Okay, now this is the initial case. Now electric field is directed in this direction. Now it is going to be bending in the direction of, its slope is increasing. Positive slope, it shows in the direction of increasing, in the direction of electric field. Now under this condition, the energy band diagram of this semiconductor, P-type semiconductor, is like this. This is under without biasing. Now this is under bias. It is like this. Okay, sorry. So for easy understanding, I am removing that lines, vertical lines. I am taking only horizontal lines. This one, this one, and for P-type valency Fermi energy level is close to EV. Now this is EC, it is EV, this is Fermi energy level, EFP. So at approximately midpoint of it, it is EFI. EFI. Okay. So when it is subjected to external electric field, that means an external voltage is applied to a semiconductor, its energy band diagram is going to be changing. Okay, now its energy levels are showing a positive slope in a direction of electric field. This is the direction of electric field. Okay, in this direction it shows positive slope. Okay, and from this doping EFP, from this EFP Fermi energy level, what we understand, for example, they given the energy band diagram of a semiconductor like this. Okay, now I am taking the next one. Let us, this is the energy band diagram of a semiconductor they given. This is the energy band diagram of a semiconductor they given. Yeah. We know this. This is going to be EC, EV, and it is EFP. Okay, EF, Fermi energy level of semiconductor. Okay. Okay. Now, three questions I am asking from this. First question is, which type of semiconductor? Type of semiconductor. Type of semiconductor. Okay. Second question is, external voltage. That means external biasing, external voltage polarities. That means external voltage or external electric field representation. And third point is it uniformly doped or not? Is it uniformly doped or not? Uniformly doped or not? Or not? These are my three questions. First of all, type of semiconductor. I am going to type of semiconductor. So Fermi energy level is close to the valency band. Based on this, I am saying it is p-type semiconductor. Based on that point, I am saying it is p-type semiconductor. Okay. Second point, external voltage or electric field representation. So if you take p-type semiconductor like this semiconductor, okay, like this. Now this is the direction of increasing the slope, positive slope. So electric field should be in this direction. So electric field should be in this direction. That means it should be a positive and it should be a negative. It should be a positive and it should be a negative. This is the external voltage or electric field representation. Okay, and third one is it uniformly doped or not? Okay, based on the Fermi energy level, based on this Fermi energy level, we can represent this. See, Fermi energy level, the separation between the valency band and Fermi energy level both are uniform here to here. Here whatever the value, here same value, here also same value. Based on this, you can say it is uniformly doped. It is uniformly doped. For example, the case is like this. EC and EV. Okay, let us I take the regular case. Later we bias it. Let us, I am taking the case like this. It is EC and it is EV. This time I will take n-type semiconductor. Now this is the Fermi energy level, EF. Okay, EFN. Now this is the EF value. Plot of EF is like this. This plot of EF is like this. Okay, and now your semiconductor point of view, this is the A side and this is B side. Now comment on the doping profile of n-type semiconductor shown in this figure. Simple. See, at this end of B, Fermi energy level is high compared to at the end of A. At A side, Fermi energy level is below this value. Okay, at B end, this is reached this value. So at B side, doping is high compared to doping at A side. This is not uniformly doped. This semiconductor is not uniformly doped because your Fermi energy level is not a straight line. Your Fermi energy level is changing. Okay, and at this B side, doped, high doping, high doping this side, and less doping at this A side, less doping at A end. Okay, that is the doping profile. Now, for example, they given a plot like this. They may give like this also, like this. So at this end, less doping, at this end high doping, but compared to the regular case, it is much close to the conduction band. That's why at this end it is heavily doped, not high. Very high amount of doping. Very high amount of doping at this end. Okay. So from the energy band diagram slope also you can identify the given type of semiconductor and the given the amount of doping what they added. Okay, and is it lightly doped, heavily doped, or moderately doped? Everything you can write. Okay, now this is about energy band concept when your semiconductor is subjected to external voltage. Okay, okay, my dear friends, don't forget to use my code during subscription VROUT 10 to get 10% discount, to avail 10% discount. Okay, and join our telegram group to get the live updates. Okay, and here is a bell symbol. Please click on bell symbol in Unacademy to get the updates of my videos, as well as give your valuable comments in YouTube. Okay, we are welcoming your valuable comments. Please don't waste your time. Whatever thing is happened at outside, your learning process should not stop. Okay, please don't waste your time, and all the best. Thank you, thank you one and all. Thanks for spending your valuable time with me.